Swayam Prabha. Digital India. Educated India.
Now, let us quickly do this math, because we have to cover a lot of ground. Okay. So, this is my paraboloid, this is the plane. So, I look at a point, say A B. So, A B goes to this is somewhere on the surface. I am first interested in is the remember L is my paraboloid. So, tangent plane at so, how do you obtain? You obtain by doing this at x equals to a, this should be 2a. Similarly, you do for y, it should be y, this should be 2b, right. So, the equation of the tangent plane would be, I checked the computation. So, I think just bear with me till I come up with them with a constant k, right. We will evaluate this constant. Okay. So, now what we do is you solve for k, mind you it passes through this the tangent plane passes through this point, right. So, replace it. So, t passes through, call this point some z, no z I cannot use, some L, call this point some L. So, t passes through L, use that, and your if you just do this calculation, k would solve to a square plus b square, right. So, the equation of your tangent plane finally is 2 x plus 2 b y minus a square plus b square. Okay. Now, what I will do is this comes the interesting part. So, what I have got is a plane that is tangential to the paraboloid at this point L. Fine. Now, what I will do is I will shift this plane which is tangential at this point L by a distance of some rho square, right. Now, if I so think of this paraboloid, there was this tangent plane, I move it up by some distance rho square. So, now it is going to cut the paraboloid, right, and what would be that intersection? Kind of an ellipse in, right. If it is vertical, it is going to be a kind of a parabola. So, it depends on the orientation in which it cuts, but with this think of a slant thing. So, if you move it up, it is kind of an ellipse. Now, if I project this back onto the xy plane, what should I get? Good, right. So, I will do this calculation. Now, what will happen is the interesting thing that will happen, for which really the lemma works, is the distance by which I pushed up the plane and I had the ellipse, projected it back onto the xy plane to get a circle, the radius square of this circle would be same as that distance, and that is the reason everything works, right. Did you understand? I took this tangent plane, pushed it up, this intersects the paraboloid, that intersection is an ellipse, right, and it is, mind you, this is like rho square up. Now, when I project this back onto the plane, it will be a circle. Now, what I will show you is the radius of this circle has a bearing on the distance by which you pushed up the tangent plane up, right. Now, you can see, I mean, say a point, I will show you something even more interesting. So, now you take this point PQR, that is it is parallel movement, yeah, it is not going to be tangential, no? If I move the tangential, no, this is this plane, right. You know, in R2 if you have a line moving it parallel to itself. So, similarly, I have a plane in 3D which I move parallel up, fine, it is a vertical movement up. Okay. Now, think of this, think of 3 points PQR, take them above, right. It will be a plane which again if you push down you can make it tangential, right. Now, the same thing will work. If you see, you take PQR, project it up onto the paraboloid, you have this P naught, Q naught, R naught, you can pass a plane through it, right. Now, this plane can be like the earlier one where I computed the tangent, pushed it up, right. So, similarly, I even can push it down to make it tangential. Then that tangential point I will make it the circle of the circumcircle of the PQR, fine. Now, this radius, so if now you have to have a point which is inside this circumcircle, the distance should be less than that amount of pushing, right. So, this is what will fall in place once we finish this calculation. Yeah, let me go ahead with the calculation, you will understand. Okay. Okay. What I now do is so, this was the equation of the earlier tangent, I have just pushed it up. So, this is the equation of the new plane. Now, let us look at L with my paraboloid. So, to do that what I do is just eliminate z. So, you have x square plus y square equals to 2 ax plus 2 by minus a square plus b square plus rho square, which obviously you understand is nothing but what is this? Equation of a circle of radius rho in the original plane, right, not on the lifted plane, in the original plane. now if you just go back and see what happened. Why it is not going back? So, here was my AB, fine. Here was my AB, here was the tangent plane. What I did was I pushed it up by a distance of, so this distance was rho square. So, this was the new plane, right. This new plane was intersecting the paraboloid. This intersection, when I projected back, I got, so this intersected somewhere, it was an ellipse. I got this circle whose radius was rho, no. So, this sort of is really the relation, that if you are taking a circle, so what is a circle? It is now, a circle is uniquely defined by 3 points, right. So, if you lift this circle up, that means lifting P to P naught, R to R naught, Q to Q naught, you will end up on the paraboloid, but also on this plane, right. Now, if you have a point S which is inside, right, it should lie below that plane, right, because its distance is less than rho square. So, it should essentially lie somewhere between, it should lie on the paraboloid, but it should lie somewhere between this plane and this plane, right. Now, so Arijit will, what he will do is he will just build up. So, this is like a very easy calculation to show you, the relation between. So, now once you have the circumcircle property, you can construct the Delaunay triangulation. Now, everything falls in place. So, lift the points up on the paraboloid, forget the paraboloid, construct the lower convex hull, right. So, the point is, as someone was asking me, if you look from the bottom, the entire paraboloid outside is visible to you, right. Think of z equals to 0 and you are looking at from say z equals to minus 1 vertically below, right. So, all part of the paraboloid would be, so if you think of a tube light there, the entire external would be visible. So, all points you can see from the bottom, lifted points, right. So, now you construct the convex hull. So, the convex hull would have a, so the convex hull would obviously wrap up, right. So, there would be something on the top also, but if you light it from below, some of the faces would be visible, but mind you, on that visible zone, each and every point that you lifted from R2 would be there. My calculation tells that, right. Now, when you project this back, each one of your faces in 3D was a face like this, right, because in your 3-dimensional convex hull you have faces, right. So, these faces can be like those faces, fine. When you project them back, what essentially you will get is, because of this circular argument, you will get triangles for which the circumcircle is that circle drawn below. So, you get the Delaunay triangulation. So, after if you have understood the basics of that lemma, from there constructing, I mean getting into the correct Delaunay triangulation is really not much. Now, one can show that, I mean forget about higher dimensions. For higher dimensions, constructing convex hull takes n log n plus n to the power of d by 2, if I am correct with a ceiling, or roughly take it as n to the power of d by 2 plus an n log n. But in 3D you can construct the convex hull in n log n time. So, what you can do is you take this point, lift up, construct the 3D convex hull in n log n time, project it back, you have the Delaunay triangulation, right. So, this is nice, kind of a nice argument which takes any set of points in RD. Now, you can do this calculation for higher dimensions, right. I did it for 3D, you can even take it for, do it on higher dimensions, and the essential thing is about that distance. that distance and the radius of the circle matches. So, this distance argument origin, I mean, if you sort of focus back when I was telling you yesterday about this connection, I said a convex hull has nothing to do with distances, right. It is kind of a global property of the point set, but Voronoi diagram and Delaunay triangulation are essentially distance based structures. Now, this kind of a fascinating relation, which tells you that if you just go one dimension above, this global property translates to a distance property in one dimension less. So, what you do is you take your point set in R d, project it up to d plus 1, construct the convex hull in that amount of time n log n plus n to the power of some d by 2, project back, you get your Delaunay triangulation. Using nice kind of transforms, you can even compute your Voronoi diagram as well. Okay. So, think of this, you took the lower convex hull, projected it back, faces there are triangles, edges there are edges. Now, think 3D and 2D. So, in 2D you know that the Voronoi diagram structure, vertices, edges, faces was linear in the number of points, we deduced, right. The number of vertices was some 2n minus 5, the number of edges was some 3n minus 6, the number of faces is linear. So, Delaunay triangulation is just a dual. So, there also your number of triangles, edges would be almost linear, right. Now, it tells you one very important thing. It tells you that the complexity, that structural complexity of the lower half, the lower convex hull should be same as the structural complexity of the Delaunay triangulation below, because it is just kind of a one-to-one map now. So, this sort of things would be explored by Arijit over 2 or 3 or 4 lectures today and tomorrow. So, this is kind of I think you should attend those 4 lectures, because that sort of give you a very this broad overview on these 3 structures in arbitrary generalized dimensions, right. So, these are kind of nice connections, and the important thing is like, so you see, if you had noticed what Arijit was doing in convex geometry class yesterday. So, the later part was this incidence, it was more combinatorial. The first half, see, he was talking geometry, right, but what he was doing? He was doing algebra. No? So, there is a nice, you can handle geometry using, and obviously you understand that doing theory on algebra is more, in a way I would say, is easier than making geometric arguments over geometric structures. No? So, this sort of connections are very important and nice. Okay. So, whatever time is left before we move on to the tutorial, let us do the topic that I was supposed to do in this lecture. Because what I felt was this topic is really not as important as these connections between convex hull, Delaunay triangulation and Voronoi diagram. Okay. So, polygon triangulation. Auritra must have talked of this art gallery problem, right? What was the previous lecture? Huh? Oh, area of rectangles, but I suppose that you talk of, oh, you do not know this art gallery theorem till now? So, the problem is as follows. You are given a simple polygon, make it as complicated as you like, and the question you ask is, this is kind of a very important question for museums, for the CCTVs are ubiquitous these days. I want to place some say cameras or guards who can see, give them infinite, give them as much power as you like, they can look around 360 degrees and as far as they like, right? Give them arbitrary power, and the question is, what is the minimum number of cameras that you need to see this entire polygon, right. Now, you would admit that if you have a convex polygon, you need 1. There are even polygons for which 1 suffices, which are not convex. You know, think of this polygon, right. So, these are called known as polygons with a core, fine. So, this polygon would also, if you have a place a guard here, it can see everywhere. Okay. Now, to solve this problem, you can really take recourse to this area computation thing that we did at the very beginning, break it up into triangles, right. So, what you can do is you can draw, we saw in the very first class that you can draw n minus 3 non crossing diagonals to break the polygon into n minus 2 triangles. A triangle is a convex object. So, 1 guard per triangle suffices. So, n minus 2 guards would suffice, but this one can bring down, because think of this, that if you have a triangle in this and if you are seeing this triangle, this guard really can see the triangles to its sides, right. And as because you have 3 sides per triangle, so this should sort of tell you that looking at a bound kind of n by 3 kind of thing, and one can show that it is tight. So, that is what the art gallery theorem would be all about, and I think Orithra would do it at some point of time. So, what it brings to us is that polygon triangulation is an important thing, that it allows you to solve many other small problems. Now, this was a long standing open problem, that if you have a polygon of n vertices and you want to triangulate it in order n time, finally, there was an algorithm by Bernard Chazelle around 1990s maybe, and it is so complicated an algorithm that people essentially do not implement it, right. But theoretically it is correct. It has a kind of a very messy analysis, you have to do a lot of, because geometry, I mean, if you are not doing geometry through algebra, sometimes you have to do a lot of case analysis to tackle many different kinds of cases. So, what I will just sort of hint to you is look at an n log n algorithm for polygon triangulation. Again, I will just give you the brief overview, the rest you can fill in the details. So, first let us look at a monotone polygon. Let me see some nice diagrams from the book that would help me, make you understand. Okay. So, here is the polygon. Hey, what happened? So, it is kind of an X monotone polygon. So, what it means is, like if you draw a y line, then it cuts the polygon. So, if you look at the intersection of a y line with this polygon, it will give you a connected component, right. Think of a line anywhere. So, the intersection of this line with the polygon is this. So, it is a connected component. But if you think of a line like this, then this is your intersection and this is your intersection, they are not connected, no. So, it is not, I would say it is not y monotone, but this is x monotone, fine. First, let us see how we can triangulate a monotone polygon in some efficient amount of time, and then we will sort of sometimes you feel these technological devices also behave randomly. Okay. So, you will have now, you understand that this polygon now has two chains, one is kind of an upper chain, the other is kind of a lower chain. What you do is you keep a sorted list of the vertices of the upper chain and lower chain, or rather keep the vertices in a sorted list from left to right, and with each vertex keep a tag whether it belongs to the lower chain or to the upper chain, fine. So, start with the first vertex. Now, it is a plain sweep algorithm, the sweep line is moving from left to right. First vertex nothing to do, second vertex nothing to do, third vertex. So, the idea would be I would be greedy in drawing as many diagonals as I can starting from this vertical. So, think of a vertical line on this going through this point. To the left I will draw as many diagonals as I can in a non-crossing way, fine. So, this is the diagonal that I draw, fine. Again the next vertex comes. So, you can draw this diagonal. Okay. Now, see, once you have completed a part, it is kind of a ER kind of structure, right. So, you can really forget about, after you have drawn the diagonal, you can really forget about this, right. So, similarly, after you have drawn this, forget about this. Then again comes the next one. Can you draw? No, no, you cannot draw to anything to the left. Then again something comes, cannot draw. Then again something comes. Now, see, something might happen like this, that this might even go up a little bit, right. Then there can be a situation where you can draw a diagonal to the same chain. It is not that always you will be able to draw diagonals to the other chain. There can be situations when you can draw even diagonals to the same chain, we will see. Okay. But for this example, let us go through. Again, nothing I can do, nothing I can do, nothing I can do. Then I come here, right. From here again draw. Now, the point is vertices from which you cannot draw diagonal to the same chain should be kind of reflex vertices, no, because that is the reason you cannot draw back those diagonals. But if it is reflex chain, then on top there should be some vertex sitting in the other upper chain from which the entire thing would be visible, right. This is essentially what happened here. So, what is happening is the part that is left has a nice structure to it, okay. So, the structure, so you have understood the algorithm, right. The algorithm is pretty simple. Sweep line, how you implement x coordinates left to right, whenever you take a point, look at all points to the left, wherever you can draw a non crossing diagonal, draw it, right. So, essentially what you had to n log and sort, and then diagonal drawing is like keep things on the stack. So, it is linear, because your number of diagonals at the end of the day is going to be n minus 3, and none of the diagonals that you are drawing are crossing, fine. So, roughly n log n you can tackle this. Okay. Now, about the proof that it really works. See, the way you have drawn the diagonals sort of cuts the polygon in this fashion. So, what it will have is, it will, so this is your V I minus 1, the vertex I minus 1, and this is your u. There can be other parts of the polygon which has already been this part has already been I have been able to triangulate. So, forget that part which I have been already able to triangulate. Remember, I was progressing with these triangulations. So, the part that I have been able to triangulate, forget about it. I am just looking at the part which is still not triangulated, and I look at this V I minus 1. So, forget about this part. I call this vertex u and this is V I minus 1. So, this V I minus 1 is the last vertex that has been processed. Now, will come V I, either it will be on this lower chain or it will be on the upper chain. But let us look at the structure that is remaining which has not been triangulated as yet. The claim is this will have a structure of a sequence of reflex vertices and an edge that cuts like this. This is the structure that will remain. That is the reason it can so happen that, if you remember, there was a case where I took this vertex. So, this was the reflex chain available, right, and I could kill all the reflex vertices by drawing a diagonal. This is one case. So, if your vertex is above, then you can kill all this reflex vertex, because this reflex chain is visible from up. Okay. There can be the other case where this chain may be of this fashion. This can also happen. This was your V I minus 1 and this is your V I. So, V I on the same chain, fine. The same structure you see, one edge cutting across, the other is a reflex chain till V I minus 1. This was your u. So, then what you again do is, there is what I said, always kill to the left. So, then what you do is, you keep killing till you can. What will happen? This zone will be killed, but there will remain again a reflex zone and a line, right. So, this is a reflex zone and a line. So, see, this invariant holds. So, I am basically working on a loop invariant which says that after having inserted a ith point, if I look back, the structure that is still remaining to my left to be triangulated has this special structure, and it will hold for all cases. There can be another case, I will finish with that. It is the case where you really cannot draw such a diagram, where even your, so this was your V I minus 1 and this is your V I, right, and this goes above. There, in this case you cannot draw any diagonals back, right. In this case, see, still it is X monotone, no? Monotonicity has not gone, though there has been change in the direction of the chain, but monotonicity did not go away. So, in this case you can draw back diagonals, still the structure remains the same. In the case where you cannot draw the diagonals, still the structure remains the same, right. Again, see, a reflex vertex, chain of reflex vertex and a line. Right. So, you had three cases, one where V I was on the top, you killed everything, again you see that edge will remain and then this structure remains. This was about a monotone polygon. So, we could triangulate a monotone polygon in n log n time. Now, one can even show that we can break any polygon into monotone polygons. The idea is nothing but this. See, if there is a monotonicity, right, then what will happen is your, let me talk of different, now it was x monotone, now let us look at y monotonicity. So, you are going to have vertices like this, no. So, this reflex kind of vertices, one can show that if your polygon is not a monotone polygon, then you will all have these kinds of vertices, right, because you need to have, mind you, you need to have a line such that the intersections are discontinuous. So, you need a vertex like this. So, you can geometrically prove it, right. So, you can prove a statement like this: a polygon is not monotone if it has, so this kind of vertex is known as, okay, this is known as a merge vertex and this is known as a split vertex. Okay. So, you can have many merge and split vertices. Now, so why I call this to be a merge vertex? Because if you are sweeping down, when you come at this line, it seems that these two edges have merged at this vertex, and if you are here, it sort of splits away. So, one can show that if you can kill this merge and split vertices, then you can get a monotone polygon. Okay. So, the idea would be something like this. I will show you for maybe just a merge vertex, or let me show you for a, anyway, for a merge vertex. Now, see, if there is a merge vertex, then your polygon would be, something like this. So, what you now do is, you look at this vertex, right. Now, if you have to kill monotonicity at this vertex, there should be a diagonal drawn from this vertex below. If it is above, the reflexivity will remain, the angle will be more than 180 degree, no. So, you have to draw a diagonal which goes below. So, what you do is look at, so look at the sweep line on this vertex and look at the edges that it cuts. One of these endpoints below the sweep line would surely be visible from this vertex, no, whatever way you draw. So, you draw a diagonal that way and that kills the merge vertex. So, similarly, you can have algorithms to kill the split vertex, and which is not very difficult to see. Now, what you have to finally prove is, so you are arbitrarily for what you will do is, for merge vertex you will draw diagonals below, and for split vertices you will draw diagonal. So, if you are not careful, what might happen? These diagonals may cross. So, you have to carefully write a proof, kind of a geometric proof, which says that in this scheme of no diagonals are going to intersect. Fine. And this you can do it in roughly, again say not more than n log n. So, in n log n time, so your algorithm would be, you take your polygon, first check if it has split vertices or merge vertices, linear time. If it does not, then you know your polygon is monotone, run the triangulation algorithm for the monotone polygon. If you have split and merge vertices, then you know that your polygon is not monotone. Then break it up into monotone pieces by drawing diagonals from killing the split and merge vertices. These are the only problem cases by drawing diagonals. Prove that your drawing is not messy by showing that the diagonals do not cross. You have broken it up into monotone pieces, right. So, how many monotone pieces you can break into, right? It cannot be many, no, not more than linear. Run the, and if you now look into the sum of the vertices of these monotone pieces, they would add up to linear, the number of vertices of the original polygon, no, right, because when you introduce diagonals, you are not introducing any new vertex. So, your sum total of polygons, so you will have now many monotone pieces, but if you look into the vertices of each one of these monotone pieces, they would sum to the number of vertices I had in the original polygon. So, now you have you have this algorithm for triangulating the monotone pieces, triangulate them, because no diagonal in the monotone piece will come into the diagonal for the other monotone piece. So, in n log n time you can triangulate. So, your area computation now, which was n square in the earlier day, has come down to n log n. Again, there are for this to really work, there has to be a detailed proof, but I sort of hand waved and give you the basic idea. Yeah. So, what I do is first I said I have the polygon, simple polygon given to me. First I identify if it has split and merge vertices. So, now it is a separate thing, you have this polygon, call that black box, triangulate. But how many? You know the number of triangles and the diagonals is linear again. No, that is what I said. How are the monotone polygons formed? Of the original polygon and diagonals, but diagonals are between vertices of the original polygon. A diagonal is not going to introduce any new vertex, no? So what? But it is going to be constant, no? Because everything is linear, no? See, if there is one vertex which has many incidences, so what does that mean? There are many diagonals coming out of it, no? But what is your total count of diagonals? So, if there are many coming out of one vertex, others there cannot be many diagonals, no? So, this entire sum would be it's if you just if you can do kind of an amortized sum to show it is totally linear, no? Because your number of diagonals is all given whatever polygonal shape you have, your number of diagonals is non-crossing diagonals is n minus 3. So, if one vertex has many diagonals coming out of it, then the other vertex really cannot, right. So, it is an n log n time algorithm for polygon triangulation, and now your area computation, placing guards, everything comes down to n log n. Okay.